So today we shall discuss about solving quadratic equations mod p, and later on we shall see quadratic reciprocity mod. So linear equations or linear congruence equations these are somewhat simple to deal with. A linear congruence equation will be of the type ax plus b congruent to 0 mod p. Like this can be solved easily because then this is equivalent to ax congruent to minus b mod p. Here this area with degree 1 congruence, that means p does not divide a, and therefore there is a bar such that a bar is congruent to 1 mod p. There is this a bar such that a bar congruent to 1 mod p. And then if you multiply both sides by a bar, and that gives us a bar x, so that is equivalent congruent to minus a bar b mod p. So for this find p, we have the equivalent congruence, and a bar is congruent to 1 mod p. Therefore, this is equivalent to x is congruent to minus a bar b mod p. So a linear congruence mod p can be solved easily. You have got a solution. So next thing is quadratic congruence, quadratic congruence. And there you will have a congruence equation like ax square plus bx plus c congruent to 0 mod p. Here again, the quadratic congruence, so p doesn't divide a. That is the assumption. And to solve this, we multiply both sides by 4a. So we are assuming that p is an odd prime. If p is even, then it is very easy to deal with the equation. Because if p is 2, then 0 and 1 are the only things to be tested. Whether 0 is the solution or not, and if 1 is the solution or not. And that's very easy. So let us look at that. If p equal to 2, 0 is solution if and only if c is 0 mod 2. C congruent to 0 mod 2. And the other possibility is 1, the complete vector stream mod 2. This is of 0 and 1, for example. So put x equal to 1 here. What is the solution? If and only a plus b plus c is congruent to 0 mod 2. 1 is the solution. If and only a plus b plus c congruent to 0 mod 2. So p equal to 2, that case is very easy to deal with, and therefore we assume that p is an odd prime. then we multiply both sides of that equation a square plus bx plus c congruent to 0 mod t by 4 times t. Multiply by 4t. OA is not divisible by P. We get equivalent congruence for a square x square plus 4ab x plus 4ac congruent to 0 or this is an equivalent congruence. Now completing the square. The Indian mathematician had used this method of completing the square or solving quadratic equations. So, 4 that is equivalent 4a square x square plus 4abx plus b square is congruent to b square. So I am adding b square to both sides minus 4ac mod t. That is, this is 2ax plus b bracket square congruent to b square minus 4ac mod t. Now, if there is a solution to the original congruence, then b square minus 4ac must be the square of something. This is called as the discriminant. B square minus 4ac is called the discriminant. Solution. It is necessary that b square minus 4ac is a square mod is a square of some integer mod b. It is clear from this that if there is a solution, suppose I have a solution 2 square minus 4ac is the square of 2a alpha plus b mod b. So that is necessary. But there will be the square of something. Suppose b square minus 4ac is square of some quantity, so conversely, if b square minus 4ac is congruent to, let us say, t square mod p for some integer t, then we get the congruence in the form 2x plus b square congruent to p square mod p. That is, now this p square you can take to the left hand side and then you can factorize. So 2x plus b minus p into 2x plus b plus p congruent to 0 mod p. So this is equivalent congruence. P being prime, this is equivalent to so P divides the product. What does that mean? P divides either the first one or P divides the second one. So P divides the first one means 2x plus b minus p congruent to 0 mod p. And does this have a solution? So this congruence has a solution different only. Either the first congruence, this congruent to 0 mod p has a solution, or this congruent to 0 mod p has a solution. Two x plus b minus p congruent to 0 mod p, or 2x plus b minus p congruent to 0 mod p has a solution. But these are linear congruences. So from quadratic we are reduced to linear congruences. And about linear congruences, we already know that the coefficient of x is not divisible by b. So since two a p equal to 1, each of these has a unique solution mod p. Now if t is not congruent to 0 mod p, so there is minus b, so minus p and plus p here. So if p is congruent to 0 mod p, then these two are the same and there is only one solution. So if p is congruent to 0 mod p, that is the discriminant d square minus 4ac congruent to 0 mod p goes to linear congruences have the same solution. And if p is not congruent to 0 mod p, then the solutions are different. Because these numbers would be different in that case. B minus p and b plus p would be different. If p is not congruent to 0 mod p, then the linear congruences have two different solutions mod p. So what is the conclusion? The conclusion is that the solution of a quadratic congruence mod B depends upon the discriminant. If the discriminant is not a square mod B, then there is no solution to the quadratic congruence. If it is square, then it can be 0 mod B, and then there is only one solution to the quadratic congruence. You can say that there will be a solution in that case. And if the discriminant is not congruent to 0 mod B and it is a square of some integer mod B, then the congruence has two different solutions mod B. Thus we get the following theorem. Let E be an R prime where P does not divide A, then the quadratic congruence ax square plus bx plus c congruent to 0 mod E has, now there are how many possibilities? One, no solution if discriminant is not a square mod B, square of an integer mod B. Second, one solution if discriminant congruent to 0 mod B. Two solutions means they are incongruent solutions mod B. If discriminant not congruent to 0 mod B and it is congruent to a square of an integer mod B, and discriminant congruent to a square mod B. You can say 0 also is a square, but we don't allow it here. Discriminant is not congruent to 0 mod B and it is a square of an integer modulo the prime B. So here, let me just make it clear here, discriminant equal to b square minus 4ac. B square minus 4ac is called the discriminant of the quadratic equation. Everything depends on this. If it is not a square, then there is no solution. If it is square but it is 0 mod B, then only one solution. If it is non-zero mod B and it is a square of an integer mod B, then there are two solutions. Now this is exactly like what we have studied for a quadratic equation with real coefficients. There we say delta equal to discriminant equal to b square minus 4ac. We say if delta is bigger than 0, then we say that it has two solutions. Okay, that is because if delta is bigger than 0, any positive integer, positive real number, it has two square roots. So here we cannot say in the case of this algorithm mod p, positive negative that doesn't make sense. For real numbers, we just write this condition of becoming a square of an element. It can be written in this form, positive. So in this case we say that there are two solutions which are real solutions, and delta is equal to 0, then there is one solution, and delta is negative. In that case we have no real solutions. The quadratic equation, and then we express the solutions in the form of complex numbers, and then we have this formula that minus b plus or minus root of b square minus 4ac upon 2a. The same formula you can get in the case of mod b also, that the original quadratic equation we have reduced to two linear equations, and these two linear equations, they are of the type 2ax plus b plus or minus t congruent to 0 mod p, where what is t? T is not uniquely determined. You can take t to be any square root of b square minus 4ac mod p, any solution mod p. So t, any solution of, we can say, y square congruent to delta mod p. That is, there are two square roots. Because once in the square of an integer, there are two square roots mod p. Any one you can take. So once you take that one, and it's negative. Okay. You get 2. And now what do you get here? That is 2x congruent to minus b. Again you can say plus or minus t mod p. And that is, now instead of dividing by 2a, we can say that we are multiplying by the inverse of 2a mod p. So that is x congruent to 2a bar into minus b plus or minus t. So it is the same formula that you get, where 2a bar is such that 2a into 2a bar is congruent to 1 mod p. That is, essentially you are dividing by 2a mod b. So it is the same formula, minus b plus or minus root of b square minus 4ac. T is what? T is square root of b square minus 4ac. Usually for real numbers we take that square root to be positive square root and give plus or minus sign. Here what you should do? You should take any square root, whichever you like, and give plus or minus sign. So formula is same. Interpretation is slightly different. Okay. So here the problem is, if you want to know how many solutions are there, you should know whether the discriminant is a square or not. Okay. This problem was not there for real numbers, because a positive real number will have a square root. Negative real number will not have a square root. So whether that number is square or not, that problem has easy solution. Here, whether an integer has a square root mod p, that is not easy to decide, because you have to really find out, list all the square roots, all the elements you take from 0 to b minus 1, take the squares of these and see whether your number is square of something. That may take a lot of time if p is large. So The problem of solving a quadratic equation mod p is reduced to deciding whether an integer is a square mod p or not. So, the problem of knowing the number of solutions of a quadratic congruence is reduced to knowing or finding whether the discriminant of the quadratic congruence is a square mod p or not. In this context, one studies squares mod p, and mathematicians have found some nice ways of determining whether an integer is a square mod p or not. And in that context, one has the concept of quadratic residue and non-residue. So definition: let A be an integer and let B be an odd one. Suppose A not comparable to 0 mod B, that is AP equal to 1, or P does not divide A. Then we say that A is a quadratic residue mod P, provided there is some integer B such that A is congruent to B square mod P. A is said to be a quadratic residue mod P if there is an integer B such that A is congruent to B square mod P. There is an integer B such that A is congruent to B square mod P. Otherwise, A is called a quadratic non-residue mod P. For a specific prime, we can find out the quadratic residues and non-residues directly. For example, take P equal to 7. Take a complete residue system like 0, 1, 2, 3, 4, 5 and 6. of these, so this is let us say x is x square. What are the squares of these mod 7? So 0 square is 0, 1 square is 1, 2 square is 4, 3 square is 9. Now 9 means 2 modulo 7. So 4 square, what is that? 16. 16 is also 2. 5 square is 25. 25 is 4. And 6 square is 36, that is 1. You see that these 3 squares are there and you get the same numbers in the opposite order. And that is not a wonder actually, because 3 and 4, they are negatives of each other mod 7. 3 is congruent to minus 4. So, if you take square, you will get the same number, mod 7. So, you see that there are 3 quadratic residues and therefore the remaining 3 are quadratic non-residues. 0 is separate, non-zero numbers mod p, they are classified as quadratic residues or quadratic non-residues. Here in the definition, we assume that A is an integer which is not congruent to 0 mod p. So, 1, 2, 4 are quadratic residues mod 7. And others are not coming as squares of anything. See that this is a complete value system. So if you take some integer outside this also, its square is congruent to one of the square listed here. Okay, suppose I take 100 square. 100 is congruent to one of these numbers. Okay, so 2 mod 7. And then 100 square is congruent to 2 square. That is 4 mod 7. So like that. So the remaining are quadratic non-residues. And 3, 5, 6 are quadratic non-residues. Mod 7. So, derivative the numbers 0 to p minus 1, 0 is separate, remaining 1 to p minus 1, these are separate numbers. In this case, we have seen that half of the numbers are quadratic and the remaining half are quadratic non-residues. Does it happen always? That is actually a few things which we can see. So, this is a simple theorem. Out of the numbers 1, 2, etc. up to p minus 1. So p the odd prime that is there, half of quadratic residues mod p and the remaining half are quadratic non-residues. Mod p. So for this, what we can do for the case p equal to 7, the same thing we should try. So note that for 1 less than equal to I less than equal to p minus 1, p minus I square is congruent to 1. So p minus 1 square is going to be 1 square. And p minus of p minus I, p minus 1 square is going to be p minus 1 square. So congruent to, so this is actually p square minus 2pi plus I square. That is congruent to I square mod p. That means 1 and p minus 1, their squares are same. 2 and p minus 2, their squares are same. From this way and this way, you get same squares. So, at most p minus 1 by 2 squares are there, not more than that. Okay. Hence, there are at most p minus 1 by 2 squares. Squares means quadratic residues. Mod p. But two squares sometimes are identical. When does that happen? Two numbers, they have the same square mod p. When does that happen? Now if you take the example of the modulus 8, 1 square, 3 square, 5 square, 7 square, they are all same, they are equal to 1. But modulo p, you will see that only squares of two different integers mod p can be equal. So, a square congruent to b square mod p holds if and only if a square minus b square congruent to 0 mod p if and only if. So we can factorize this a minus b into a plus b congruent to 0 mod p if and only if first thing is 0 mod p or second thing is 0 mod p. If and only if a minus b congruent to 0 mod p or a plus b congruent to 0 mod p. And this means b should be congruent to a and this means b congruent to minus a mod p. If and only if b congruent to a mod p or b congruent to minus a mod p. Here we have used that p is prime in this step. Here we have used in this step p prime. That's why either this is true or this is true. So b can be either a mod p or b congruent to minus a mod p. So at most two different elements mod p, they can have the same square. So a and minus a, they have the same square and no other element has the same square. A belongs to this set 1 to etc. up to p minus 1, then A is not congruent to minus A mod B. A and minus A are different. Because what happens if A is congruent to minus A? It would mean 2 times A is congruent to 0 mod P. That is not possible because P is odd prime and A is already in the set 1 to B minus 1. Or otherwise, to A congruent to 0 mod P. And this is a contradiction as P is odd. P is odd prime. As P is odd prime. So these are unequal. And therefore, one square, 2 square up to b minus 1 by 2 square, they are all different squares. Hence, 1 square, 2 square, etc. b minus 1 by 2 squares are different squares mod P. Okay. Because if two of them are congruent to each other, I square congruent to a square, what should happen? I should be congruent to minus z, or I should be congruent to plus z. But if you take numbers from 1 to b minus 1 by 2, then I congruent to minus z means I plus z is 0 mod p. That is not possible. Okay. These are numbers from 1 to p minus 1 by 2. So, two of them if you add, you cannot get a number divisible by p. So, they are distinct. And thus, these are all the squares mod p and exactly half are squares. So, if you take the remaining numbers like p plus 1 by 2 etc., they are like p minus I. So, their squares are equal to one of these. And therefore, we get exactly p minus 1 by 2 squares of quadratic residues. Mod p. So basically it is a square congruent to b square, difference is either b equal to a or a plus b is 0 mod a. That's what we are doing. So 1 square, 2 square, 2 square are different mod a. And no additional square is possible because if you square p plus 1 by 2 etc., you will get one of these. So these are exactly all the different squares of quadratic residues mod p. Now, how to decide that a specific number is a square mod p? So, natural method is you have a list of squares, see that your number is in that list or not. You already have listed 1 square, 2 square up to b minus 1 by 2 square. This is possible for a small value of p. If you just take t equal to 30, you can just list already these squares, mod 30, and I can decide. But if p is very large, then this is not a good way. Suppose p is a 50-digit number. if it is such a large prime is there, and then you have to take the p minus 1 by 2 numbers, 1 to p minus 1, take the squares of these numbers and see whether your number is one of these. That will take a lot of time. So people are very interested in finding some method to decide whether the number is square or not mod p, which was very simple for real numbers. Positive means it's a square. Okay. So here what should we do? So Euler has a criterion. So let T be an odd line. This odd line is essentially there always odd line, and A not congruent to 0 mod p. Then A is a quadratic residue mod p if and only if A raised to p minus 1 by 2 is congruent to 1 mod p. If A raised to p minus 1 by 2 is congruent to 1 mod p, then A will be quadratic residue. Otherwise, this will not be 1, but it will be minus 1. So, otherwise, A raised to p minus 1 by 2 is congruent to minus 1 mod p. Thus, A raised to p minus 1 by 2 is congruent to 1 mod p if A is a quadratic residue mod p and it is congruent to minus 1 mod p if A is a quadratic non-residue. Mod p. That means non-residue means A equal to b square, such a b does not exist. A congruent to b square mod p. This is the criterion of Euler. And here you may say this is a complicated criterion, that you have to find out A raised to b minus 1 by 2, so a very big power. If E is large, then this is a very large power of A. But still you can understand that it is far simpler to carry out this A raised to b minus 1 by 2 as compared to listing all the squares and then see whether your number A is congruent to one of these squares. So that way, for a specific number, if you are interested in knowing whether a specific number is a quadratic residue mod p or not, it is good to take the power of this, and moreover, powering is not considered difficult because you can use repeated squaring. Powering can be done somewhat easily by using the method of repeated squaring. So you find out A square mod p, A raised to 4 mod p, A raised to 8 mod p, and then write your number as a sum of powers of 2. Like A raised to 100, you can write as A raised to 64 into A raised to 32 plus multiplied by A raised to 4. And then repeated squaring can be used. So it is not considered difficult to find out this. So this Euler's criterion is useful that way. So let us now see how this works to prove. Suppose A is a quadratic residue. Mod P. Therefore, there is B with the integer B such that A is congruent to B square mod P. Now raise both sides to P minus 1 by 2 power. A raised to P minus 1 by 2 is congruent to G square raised to P minus 1 by 2. But this thing is B raised to P minus 1 mod P. But now A is congruent to P, so B is also congruent to P. Because A is congruent to B square. So what is B raised to P minus 1? By Prof theorem, B raised to P minus 1 is congruent to 1 mod. So this is congruent to 1 mod P by Fermat's little theorem. So one way we are done. Okay, now suppose so A is not a quadratic residue mod P. So if it is a quadratic residue, then A raised to P minus 1 by 2 is congruent to 1 mod P. You can also do it this way, that suppose A raised to P minus 1 by 2 is congruent to 1 mod P. Then we show that A is a quadratic residue. So conversely, suppose A raised to P minus 1 by 2 congruent to 1 mod P. So here, one of the methods is to use primitive root mod P. So let G be a primitive root mod P. So once you have a primitive root mod P, its order is maximum possible, that is P minus 1. G has order P minus 1. Order of G mod P is considered as P minus 1. Now, any integer is congruent to one of the powers of G. The powers of G are distinct. One G square, or you can take G square, etc. G raised to P minus 1 are incongruent mod P. And therefore they provide reduced string mod P. They are P minus 1 in number, they are congruent to P, they are incongruent, therefore they provide reduced string mod P. And A is congruent to P, so A must be one of these mod P. Therefore, A is congruent to G raised to I mod P for some I, we can take 1 less than equal to I less than equal to P minus 1. A is congruent to J raised to I mod P for some I. Now, substitute that in the previous equation, that is G raised to I times P minus 1 by 2 is congruent to 1 mod P. Since order of G is P minus 1 and G raised to this number is congruent to 1 mod P, that means the order of G has to divide this number, that is P minus 1 divides I into P minus 1 by 2. Okay. Now this is the multiple of P by 2. By what? I by 2. That means I by 2 must be an integer. Okay. That is I by 2 is an integer, say Z. Therefore, I equal to 2Z. Therefore, A congruent to G raised to Z, G raised to I, which is congruent to G raised to 2Z mod P. So take B to be an integer such that B congruent to G raised to Z mod P. Take this as B, any integer which is congruent to G raised to Z mod P. So what is B square? B square is congruent to G raised to 2Z. Therefore B square is congruent to G raised to 2Z and that is congruent to A mod P. So A is a square. Therefore, that is A is a quadratic residue mod P. So this is first part, that A is a quadratic residue mod P if and only if A raised to P minus 1 by 2 congruent to 1 mod P. So suppose A is not a quadratic residue mod P. Therefore, by this argument, A raised to P minus 1 by 2 is not congruent to 1 mod P. But A raised to P minus 1 by 2, if you take the square of this, that is congruent to A raised to P minus 1, which is congruent to 1 mod P. Therefore, A raised to P minus 1 by 2, so P is a prime. As P is prime, A raised to P minus 1 by 2 is congruent to 1 or minus 1 mod P. Okay? Because extra congruent to 1 mod P are either two solutions, both are minus 1. And therefore, it is not 1, therefore it must be minus 1. Therefore, A raised to P minus 1 by 2 congruent to minus 1 mod P. That's what we